Good morning. Thank you for coming to this wonderful facility to see this program. I am glad to be able to kick it off, and I want to talk a little bit about innovations from space. And I'm going to try to stick to my time because we have a wonderful program today, and I don't want to slow it down at all. I'm going to start just to introduce space a little bit to you. In order to get to space, there are innovations that are required just to get up there in terms of propulsion. To live in space, you need life support systems. And then there are innovations associated with that. And then the best thing of all are those innovations that occur in space that can benefit human beings back on Earth. This picture, by the way, this is of the Space Shuttle Endeavour, as taken from the International Space Station. It's about, I'd say, about 12 kilometers in trail. That's an orbital sunset, and that's the final point before the shuttle would begin its rendezvous with the International Space Station. To talk about the International Space Station a little bit, it is about 400 kilometers up in space. It goes around the Earth about once every hour and a half. It weighs about 400 metric tons. And I'm going to tell a little story about these solar arrays here. They figure in innovation for today. They generate about 160 volts of direct current, about 80 kilowatts of power. That's enough power to run all the life support systems and all the experiments on the space station. But they're very flimsy. They're very lightweight in order to make it to orbit with a minimal amount of propellant. This is a film of how those arrays are supposed to expand. We had to do this on my first flight. The normal extension goes like that. It telescopes out, and you can have some stiction between the array as it's extending. That's not what happened to us on our flight, though. As we were extending the array after assembling it, we had a guide wire that snagged and tore the array. In this condition, the space station was broken, and we could not separate from the space station. We were stuck on the space station until we figured out a fix for this. This is another view of what that looked like. So there was let's see, I don't think the laser makes it through. There's a guide wire essentially right here that snagged and tore this hole in the array. That's about my height. That's about 5 to 6 feet across, so that's bigger than it looks like. And as I had mentioned before, it was a problem for us because when the shuttle departs from the International Space Station, there are stresses that are on those arrays that needed to be addressed. So, question to you, as innovators, what would you do? How would you solve this problem, and how would you go about it? But I'll get back to that and talk a little bit about some of the innovations that do occur in space. Space, the temperatures are they vary from plus 200 degrees in sunlight to minus 200 degrees in shade. We travel at a speed of about 8 kilometers per second. That's 25,000 feet per second. But essentially, that's about 10 times the speed of a bullet. So if you impact anything, even a grain of sand could inflict tremendous damage. So there are innovations that are required to get into space, to live in space, and then some of those we can take advantage of back from space. One of those that kind of fit into the two categories of required to get into space and then we benefit from it are these microsensors. We're benefiting from Moore's law in terms of the number of transistors or electronic components that we can put on a single chip. Those get smaller by about half, about every 2 years. And so we are able to develop these sensors initially for probes that would go to Mars to deploy landing bags or parachutes or rocket engines to allow landings on Mars. We have them now on Earth to deploy airbags in cars, and probably most prevalently we have them in our little iPhones and other small electronics to allow us to rotate the screen when we move our screen around, and also to navigate just using our phones. Back in the days of Apollo, when they were building those structures, they needed to understand how rocket engines and different stages would stand the stresses from heat and acceleration and the different loads as a rocket went up into space. Rather than build those rockets and test them, that would be very expensive. What they decided to do was to build them in a computer with a process called finite element modeling, so that they would cut this rocket up into little pieces, and then with those little pieces they would determine how each piece would interact with each other. So what does that look like now? How do we benefit from this? Well, we use that same process now to build cars and boats and skateboards. And even in the entertainment world, I think someone had a slide of this before. When you see computer graphics imagery, you are seeing a model of a human being that is being used to mathematically generate a cartoon or an animation of a human being. So we see this every day. Microcapsules, I like this story because in exploration you don't know how things are going to turn out. Microcapsules can be developed in space because there's a minimal influence of gravity. There's a microgravity component. You do see gravity, but it's at a very, very low level, which allows for very pure spheres to be developed in space. And NASA did this early in the Space Shuttle days. These microcapsules that were developed in space are now used as standards for very small microcapsules. And then later the manufacturing was changed for allowing these to be developed here on Earth. It is a story that isn't over yet, and as is the case with a lot of innovation, you don't know what the end result is. And one of my favorite quotes from our American inventor, Thomas Edison, is that I haven't failed, I've just found 10,000 ways that don't work. And so you encounter a lot of that, and this was not a failure, it's just that the envisioned manufacturing in space did not occur with this particular microcapsule. However, we did benefit from the research. This is something that I think is wonderful. With the ability to shrink electronics, we're now able to launch very, very small satellites. So whereas in the early days, satellites had to be very large, very heavy, and do a lot of things, you can now launch, these are nano satellites. They're essentially 10 centimeters around and 30 centimeters long. And they can do communications, they can provide observations of Earth, and you can launch large numbers of them from rockets. So this enables us to, for instance, take more real-time images of Earth. So this is a wonderful technology and an innovation that came about because of things that have happened on Earth and what we know about what we can do in space. In order to get to space commercially, and in order for companies to be able to do this and survive, they have to be able to make a profit yet maintain safety. So this is one of the challenges that they're undergoing, is the development of rocket engines that are less expensive. This is an engine that's being used by Virgin Galactic for space tourism. This engine, the airplane is released from a carrying aircraft, the engine's fired, and then this rocket will fly into the very lower regions of space and then return back as a glider. Another development are the self-landing rocket engines. This is an example from SpaceX, where they will take a payload into space and then they'll bring the first stage back and land it on a barge. The benefit of this is those rocket engines are very, very expensive to develop. The pumps on there rotate at thousands of RPM, and up until this point we were just throwing those away, unless you were talking about something like the Space Shuttle. But in this case, the stage comes back. Not only can you reuse the engine, but you can look at the engine and the stage and see if there was anything that happened during its flight that you can learn from and improve the design. Other things that happen in space, we do this as a matter of routine from NASA. We have mission control, of which the function I would serve when I would be there would be this Capcom role, kind of in the very bottom of the picture, where you have an entire team of specialists that are experts in heating and power, in communications, in navigation, and they would communicate as a team through the Capcom to the crew, and so that it would be one big team. But part of that challenge was keeping the whole team together, because the whole team combined is a few hundred people that are operating continuously, and it is dependent on the skill of the communicator in order to make sure everyone understands what the others on the team are thinking. Training and entertainment in VR. So here are a couple of astronauts that are on the International Space Station, and they're enjoying virtual reality. And we actually use this to train and to design. So before we go on certain spacewalks, we have astronauts that put on the virtual reality equipment, and then they rehearse their spacewalks with the VR equipment. And also when we're building modules for crew members, we can build it in a computer. The crew members can put on those goggles and pretend like they're in the module itself. Telerobotics and remote operated capabilities. You have the Mars rovers that are on Mars, and they have continued to serve well beyond their designed life, which is a wonderful opportunity for observing the Martian surface. And then we also have telerobotics, where it is safer in many cases to take a robot out and do the work that you would have a human being do because of those dangers that are out there in space, the changes in temperature and the micrometeorites that can do great damage. So we've been working for a while, not just NASA, but other partners in industry to develop robotics. Remote operations. One of the considerations when we go to, let's say, Mars, is the ability to keep our crew members alive. We usually do fly with a doctor on board, a trained medical doctor, but what about the case if he's hurt or she is hurt, and then the surgeries need to be performed on them? Well, we can do telerobotics. We can have a doctor that is able on Earth to manipulate surgical equipment, and then up on the space station or the spaceship, that equipment is operated mechanically in order to perform the operation. Social media in space. This is one of the big things that they do on the International Space Station. It's probably one of the best things they do is they have the astronauts tweet, send pictures, share their experiences of what they're seeing up in space with folks on Earth. As a matter of fact, this is a good time for me to remind you that if you want to, has anyone seen the space station fly overhead? Okay, a few people have. If you want to look, if you type in "spot the ISS" into your search engine, you'll be taken to a NASA site that'll tell you where to find the International Space Station. Tonight, there are two opportunities for those that happen to be outside at 9:32 p.m. There'll be a pass from the west-southwest that'll depart out to the east at 9:32. It should be about 60 degrees high. And then again at 11:08 in the evening, a little bit later, it'll be another pass very high. But these folks often, we have pictures of Warsaw and other places in Poland that are taken and shared on these sites.
Hey guys.
Good morning from the International Space Station and from the Space Shuttle Endeavour, Mr. President.
Well, it's great to talk to you guys. I wanted to, first of all, just say that we've got a bunch of very excited young people here with us, along with a bunch of somewhat excited teachers. We have one engineer and one member of Congress. So yeah, you've got and a whole bunch of press here, so it's a pretty motley crew, and one president.
Two astronauts are from Maryland.
but I just wanted to let you guys know how proud we are of all of you.
So that was obviously a very special phone call to get up on the ISS. The pity for us is whenever you see something like that from space, all we are essentially looking at is about an inch large lens on a small video camera that's on a tripod. So the grandeur of hearing from the president is a little bit lost on us. However, the main point is that because of satellite communication, we are able to carry on conversations. And I could even, when I was up there, call my wife when she was at home. She had an iPhone, and when I would call her, it would never be at the greatest time. It would be a call from an unknown caller, and on a hunch, she decided to accept the call, and then it was me calling from the ISS. So that was a nice thing to do. I put this up as a model, perhaps, well, it's a comparison of how NASA develops ideas and how perhaps there is a parallel way to do this in the NGO realm. On the right is the NASA Technology Readiness Level Scale. It essentially starts at the bottom with an idea or an observation. Then you test the observation. I'm going to just walk over here. Then you test the observation to see if it works, if it's a true observation. Then you test it, you demonstrate it in a relevant environment. You might put it in a laboratory. You might put it in vacuum. You might put heat on it to make sure it still works. And later you test it in flight. And after it's tested in flight, if it involves human beings, then you can test it with humans on board. And then when you've got a good human test, you're at technology readiness level 9. So my idea for perhaps if you're generating ideas is to create the idea, prove that it works, have a simple experiment to make sure that the process that you think is occurring, in fact occurs, demonstrate it in a limited, controlled environment, then give it a test drive, maybe a larger pilot program, and then later when you're complete with that, it's ready for use, and you can use it on a large scale. Okay, so back to my story about the solar array that was torn. NASA, the way NASA solves problems like this is they have something called Flight Control Team 4. There are normally 3 flight control teams that are operating continuously. They go on 8-hour shifts, and they have a 4th one that is on standby that has it's multidisciplinary. They have all the experts available, and they operate as a large team, and they get together and they come up with solutions. The solution they came up with for this particular case was something that they called cufflinks, and that they sent instructions up to the space station, and I was one of the guys that got to build it. But they're about 6 feet long. They're used, it was just electrical wire that we wrapped insulating tape around, and then EVA tape so that the spacewalkers could go out and perform this surgery on the space station. And here's kind of how that went. So you can see us making the cufflinks in the upper left. We got the robotics folks figuring out how to get the spacewalker out to the array, and they went over the procedures of the array repair itself and got the EVA suits ready. One concern was the voltage. You can't turn the electricity off in the array. It's 160 volts live. So when we did send our spacewalker out there, you noticed he had insulated tools, a hockey stick that kept the array from touching his suit. Inside his suit was 100% oxygen, so that was a very dangerous situation. You didn't want a spark inside there. And fortunately, he was our doctor, he was our surgeon, so he performed surgery on the space station for us. And the really neat thing is once those cufflinks were in there, they were the exact perfect length. The ground really knew what they were doing, and they're still up there. So if you see pictures of the International Space Station, you can see those cufflinks attached to that array.